Paul, thank you very much for the introduction, and welcome everybody to this second webinar in our series of 4 on using the 2012 Wood Frame Construction Manual on determining wind load distribution in buildings. Today, we're going to focus on load paths. Last week, as you remember, we were in a more general topic of how to use the wind maps and what the changes were in ASCE 710 and how those changes are reflected in the Wood Frame Construction Manual. Next week we'll talk about connections, and the following week we'll talk about how to take these loads to the foundation. So again, welcome everybody, and thanks for attending. Just a reminder, you saw this slide last week, but
what has he tried? What has he tried?
So hopefully everybody can still hear me okay. There is some information here about copyright materials, and if you decide or want to use the materials in this webinar, you do need to get permission from the American Wood Council. Just some information about learning objectives, what we would like for you all to learn as part of this webinar, and obviously we would love to hear your feedback and or questions about this to try to make sure that the material covers the information here that we thought was important about load paths. But we'd like for people to be able to describe how load paths and loads are distributed to buildings both vertically and horizontally, be able to describe several different load paths that are critical to improving building performance, be able to recognize some problems in building framing that might present construction challenges, and to be able to recognize construction defects that could potentially fail under high wind. So hopefully we will have covered all those topics at least as adequately as we can in a 45 or 50-minute webinar. Again, we're using the Wood Frame Construction Manual as the basis for today's presentation. It is the 2012 version. We talked about this just a little bit last week, that we are using primarily the prescriptive provisions in Chapter 3, and those provisions cover connections, floor systems, wall systems, and roof systems. And so today you will see some examples of loads taken from the tables in Chapter 3 and some examples of some figures that are also coming from that same set of prescriptive provisions. So here's what I'd like to cover. The topic is load paths, so what we want to do is to take a look at both vertical and lateral load paths, and to look at the vertical load path from the roof to the foundation, and to look at lateral load paths as loads are accumulated on vertical walls and roofs, and how those loads also get to the foundation and the soil. Obviously, our attempt here is to describe the methods, but more importantly probably the issues in trying to make sure that loads in fact can be disseminated through the building frame and get to the soil so that those loads can be dissipated. That's our primary job in most structural engineering applications for buildings. Wind just presents us with a couple of other challenges, and so those are the ones that we want to focus on today. I think we saw this graphic last week too. So you see several areas where, several areas where wind is impacting the building. So you see, hopefully from my pointer, the direction of the wind assumed in this little graphic, applying loads that create uplift on the building roof and the building frame, and lateral load along the foundation. So you see this red arrow here along the right side suggesting a shear load along that wall. In addition to that, we have some connections that are important. So the roof-to-wall connections need to be part of the vertical load path to resist the uplift from the roof, and those show in this one circle that I'm circling near a window or a door header. In the case of the corner, it's an uplift connection between the roof and the wall itself. And then, obviously, to follow that load path down, there needs to be an adequate connection between the wall and the foundation. So The connections we're going to talk about next week. The load path and how loads can get transferred through the building is what we will focus on today. So this graphic happens to come from FEMA. I believe it comes directly out of FEMA's Coastal Construction Manual, and you will see several graphics today that are being brought into this presentation from the Coastal Construction Manual. I'll try to point those out as we go through so that if you want more information about where they come from and or how they were used in that particular document, you'll know where to find it. But the graphic here illustrates at every red dot there's a connection, so there has to be somehow a physical connection made between two elements in order to tie it together. A connection can be nails, it can be screws, it can be a mechanical connector, it could be glue, but somehow these pieces of the building need to be connected to each other, and the red dots in this graphic just illustrate those places, at least in this one load path, where those connections would need to be made. So you see, excuse me, you see at the top a connection between a rafter and a ridge beam or a hip roof rafter. In this particular case, the load goes down this hip rafter. There's another connection here between a rafter and the hip. Goes across the header of the window, down to the connection between the header and the wall, down into the bottom of the wall and the second floor, across the floor system to a header on the first floor, and then down into what's illustrated here as a pile foundation. So lots of load paths in a wood frame building because there are lots of pieces to connect together. And as I mentioned, we need to get this load path to end in the supporting soil, and so we can dissipate the loads. Any place where there's a discontinuity or a weakness in the connection someplace could be a possible place where the building could fail. Now, that's the bad news. The good news is that there's so much redundancy in wood frame construction that one poor connection is not likely to cause a particular failure, but if it's a poor connection in the wrong place, it definitely could contribute to a serious load path continuity collapse issue from a very high wind. So just to kind of state the obvious for a second, we are obviously talking about load paths and design sequences, and you all know that we design from the top down. We have to take loads as they accumulate down a building. Wind loads are included, but they have to include seismic loads if the seismic is a natural hazard constraint. Dead loads, live loads, snow loads, whatever loads are applied to the building, we do that from the top down. But we build from the bottom up. So at least from looking at load paths as they are built, sometimes it's not quite so obvious that there could be a load path continuity issue until you get it built all the way to the top. And I know that I've done enough inspections, and I'm sure you all have too, where you would think that some concentrated load would be easy to be picked up in the framing and it would all be gotten, all be done correctly. But because it's being built from the bottom up, sometimes there can be a disconnect between places where loads need to be carried and having a member there to actually carry that load. So I know it's stating the obvious, but it's just something to keep in mind as we go through the webinar, and certainly as we all do designs and inspections, etc. The material today is brought to some extent from this section in the Wood Frame Construction Manual, and you can see the section referenced in Chapter 3. Deals with lateral and shear forces as well as uplift and overturning of the building and places where we need load path connections. So this information is covered in section 3.2 of the manual, and while I'm only going to highlight a few what I think are crucial statements in some of these sections, I certainly referenced them to you for your own reading and follow-up, and just make sure I have covered all the important issues. So let's start with roof systems. There's a section in the Wood Frame Construction Manual that deals with roof systems. In the roof framing section, the item that caught my eye to just highlight is that there can clearly be open framing plans in roofs, certainly in residential buildings these days, that would eliminate collar ties or ceiling joists. And when that's the case, you need to have a ridge beam. You need to actually have a beam in the roof system that would carry the load. And instead of just having a ridge board where the load is expected to be transferred across the board from one plane of the roof to the other, when you don't have collar ties or ceiling joists, that element needs to be a beam. The roof sheathing needs to be fully supported by roof framing members. Seems like an obvious statement, but there's a tremendous amount of roof framing out there, roof sheathing, that is not fully supported by a framing member of one sort or another. The sheathing edges have to be supported by blocking or edge clips. So this is an important issue to remember, certainly in a high wind area. And then when wind speeds are greater than 130 miles an hour, the roof diaphragm has to be braced with blocking and nailing at panel edges so that those loads are transferred from one panel to the next. So this it highlights what needs to be done, again, when wind speeds are greater than 130. And remember, these wind speeds now are the ultimate or strength design wind speeds from ASCE 710. So let's look at an example of a roof sheathing to framing connection. This graphic, again, comes from FEMA's Coastal Construction Manual, available on FEMA's website. The nailed connection of the roof sheathing to the roof framing is what's called the first link in the load path here. So the connection of sheathing to framing is link 1. The design considerations about this particular start in the load path are that that connection, that nail typically, needs to have enough strength to resist withdrawal of the nail from the framing or a head pull through or pull over when the sheathing pulls up over the head of the fastener. So typically that means the nail can't be overdriven. There needs to be enough head of the nail pushed against the surface of the roof sheathing to hold that sheathing down in place. And the nail needs to be long enough and have a diameter such that the withdrawal capacity will resist the pullout. So those are the two important design considerations for roof sheathing to framing connection. Now obviously, I guess I should have probably mentioned, you also have to have the nail actually strike and land into the rafter or truss. Maybe that's kind of obvious, but there are a tremendous number of examples where the framer with a nail gun in his or her hand walks the roof, nails the roof, and because of all the other sounds and noise around him, doesn't pay a lot of attention to whether that nail actually strikes into the rafter or truss or not. So first it needs to hit it, and then when it hits it, it needs to have enough withdrawal capacity and needs to not be overdriven. Link number 1. In the wood frame construction manual, there is a table. You see the number here for exposure B that provides a nailing schedule, if you will, for roof sheathing. Now what you're seeing here are roof rafter and truss spacing numbers over here in this left-hand column, and you see minimum panel thicknesses in inches for these grades of panels based on the wind speed. So you can see there's not a tremendous amount of variation in panel thicknesses until you get to 140 miles an hour and wide rafter spacing. So there's not a lot of variation necessarily in the roof sheathing thickness requirements for high wind areas. The nailing requirements are in another table, table 310, and you see the sheathing location. So you're either in an interior zone or you're in an edge zone. You see the rafter lumber material is specified by specific gravity, so it's in this column here where G is mentioned. And you see the rafter or truss spacing in inches, and then for various wind speeds you see the nailing pattern here. So E is edge, F is field. So when you get to, let's say, 140 miles an hour, which was an example we had last week, and you have a 12-inch rafter or truss spacing and you're in the edge of the roof, then you would have a 6-inch on center edge requirement nail and a 6-inch on center field requirement nailing. And you see what the nail size is. Common 8-penny nails or 10-penny box nails. Okay, let's take this to the next load path point, which is the roof framing to the exterior walls. So now we're taking the load to the exterior walls. What we need to do is we need to have a connection that will take that load to the double top plate of the wall. That is pretty hard to do with anything other than a mechanical connector. If you try to put enough toenails in a rafter or truss to get total connection for really high winds, you would typically split the rafter. And many truss members aren't big enough to really put too many toenails in. But so this illustrates a connector, and that connector needs to attach to both top plates so that in fact the load is transferred not just to the top plate but to the really top of the wall. The typical way this is done is with a mechanical metal connector as illustrated in this photograph right here in these red circles. It's illustrated here with this connector in this figure, in this sketch. The fastener schedule ought to be called out for in design plans, and so the engineer of record needs to say the roof-to-wall connection needs to be H2.5 clips on every rafter, or whatever the size designation is for a roof-to-wall connection type, to carry and take care of the loads that are being carried from the roof into the wall. This is a different wall system. This is showing masonry, but the issue is the same. So in this particular case, it could be done one of two ways, and both ways here are illustrated. One is having the rafters or trusses sit right on top of a concrete bond beam, at least as illustrated in this masonry wall, with a strap that comes out of the top of the bond beam and goes over the top of the rafter to create that load path connection. The other way, and one that I think is more typical because it's a little easier to sometimes be able to make adjustments in the framing, is to put a sill plate, if you will, or a pressure-treated top plate on top of that wall, anchor it into the bond beam, and then take a strap from there. Now you notice that in the left-hand figure here, this probably illustrates more of what you might have to do in a retrofit situation, because you have a strap attached actually to the masonry wall as opposed to anchored in the masonry as you see here. But either way, the important part is the connection. The connector needs to be adequately secured to the wall and needs to obviously have enough length and strength to go over the top of the rafter and secure the rafter or truss to the wall. It looks like this in a sketch, and you see the figure number in the upper left-hand corner. And you see some strap or connector types here. So one connector is actually being shown connecting to the truss and then connecting to the top plate, and the second one secures the two plates to the wall stud. So this clearly illustrates a continuous load path from the top of the rafter or truss to the wall system. There are three loads here that we have to be concerned about. There's the uplift load, shown obviously with the red arrow pointing up. There's a lateral load that comes into play, which is the load that's perpendicular to the wall system. And there's a shear load that is parallel in plane with the wall. So most of the time, this roof-to-wall connection has three different load components to it, which are really important to remember when you're picking connectors, when you're looking at the loads and then picking connectors. And we looked at connections last week. We looked at loads last week that had, in fact, three elements to them. All three of these loads were shown in a table from the wood frame construction manual for uplift, lateral load, and shear. And those loads are what we would take to a connector table if when we're getting ready to find a connection method. Here's an example of an uplift failure. You can see how the foundation obviously is still standing, and the roof was taken off, and when the roof lifted up, it was also pulled the rest of the wall with it, or wind pushed the rest of the wall over. But I characterize this as a wind uplift failure and not a flood, because if it had been a flood failure, all the rest of this building would have been gone as well. So this is a wind uplift failure as a result of a coastal hurricane. One other element about these loads that's important to point out, and that is that, there, as I mentioned, there is a shear load in this roof system. This picture comes from Simpson Strong Tie, so it's coming from a connector manufacturer, obviously. And you can see the direction where the shear load is being applied. There are several schools of thought about how to do this. This illustrates simply one of them. You see a rafter here or here. You see blocking, solid blocking in between the rafters, which is resisting the shear load. It's carrying the load from this rafter to this rafter. And then the shear resistance is being handled by this one connector. Now, if you had a connector that was attached here that was strong enough in all three directions to resist the shear load, then you wouldn't need this, and you wouldn't need this. If the rafter is very tall, I know one of the concerns in the industry, if the rafter is very tall, while you might have a connection that is good down here, you could still get the rafter to roll over potentially if there was enough shear load. So I'm not going to go into any more detail than that at the moment. It's a topic that we could probably spend a whole webinar talking about. But it is an issue that as designers and building officials we need to keep our eye on. Is that shear load adequately being taken care of at the roof-to-wall connection? Okay, let's take a look at floor systems now. Floor systems are covered in section 3.3. There's discussion about floor joists, both stability, and there are some restrictions on cantilever lengths. There are descriptions about how and what the size of sheathing needs to be, and what the size and the spacing of nails need to be. And again, there's a particular description about wind speeds of greater than 130 miles an hour and how this diaphragm needs to be blocked and nailed at edges to be able to resist the diaphragm action. There is a graphic, figure 37B, that illustrates the blocking that is expected to occur in the floor system, and you'll notice that this isn't at an end wall. The blocking is occurring at two joist spaces, and so that's shown in that section AA. It is expected that when the blocking gets into basically it's the third joist, the second joist in, but the third joist, that load in that diaphragm is being dissipated enough into the floor system that you don't need to carry the blocking any further than two joist spaces. One other issue that comes up pretty frequently, at least it does during inspections, and has some load path continuity issues with it, and that is that when you have I-joists like you see illustrated and installed in this picture, most manufacturers require a squash block to be installed where you see this red arrow, and that squash block is installed to prevent the web of these I-joists from buckling. Now, if you had a really short I-joist, this was only 6 inches tall or 8 inches tall, you're less likely to get buckling in the web of that joist, so obviously the taller the joist, the more that issue might occur. It's also possible to, instead of having a rim board out here that's just a sheet of OSB, which is what's illustrated in this picture or shown in this picture, you could have a more solid rim board where you could nail from the back side of the rim board into the edge of the I-joist and solve the problem that way. So this can be handled, this particular issue can be handled more than one way. Okay, let's take a look at wall systems. So we have studs now that have limitations on wall heights, requirements of attaching headers to studs to accumulate or accommodate the loads, and there's a limitation on notching the stud so we don't take too much strength out of a wall stud. These systems are all described in section 3.4 of the wood frame construction manual. There are double top plate splice requirements for walls, so meaning depending on the wind speeds, there's a splice length requirement, and that's to make sure that the diaphragm stays together. There is wall sheathing coverage and nailing that's specified for shear walls, and hold downs required at the end of shear walls to resist overturning of the loads. So a couple of examples of issues with walls. The person and the picture on the left is a really good illustration of an easy way to figure out how well the wall is nailed. Sometimes if you just go push on it in the middle of the wall, you know, it might very well be nailed in the center and you don't really see or it's not obvious that there are issues with the nailing. But you put your foot against it, and obviously in this picture you can see there's no nails at the bottom of that piece of sheathing for at least 2 stud spaces. And if that is, or you know, is intended to be or act as a shear wall, that's a problem. And then you can see some connectivity issues in the right-hand picture. Nails that are called shiners, you know, that have come through the sheathing and not attached at all to the studs, and a connector that's only got a few nails in it. Another connector that is pretty inadequate in terms of its ability to transfer a load from one part of the building to another. Here you see a connector with 6 or 7 holes in it. There are nails in 2 of them, and both of those nails are bent, so they were never adequately driven into the wood. Pretty serious inadequate connection issue in that particular example. So a couple of other elements that we've briefly covered in terms of what's in the wood frame construction manual. A couple of other elements now about the load path continuity and where the load paths need to go. So another part of the load path is we have transferred, in our discussion, we have transferred load from the roof to the wall, and we've done it with this connector. So now we have to make sure that the wall is staying together and the top plate is connected to wall studs. So there's multiple ways to do this. This link is illustrated in this red oval. So it can be done with nails and the panel sheathing, nail of the panel sheathing to the studs. Or it can be done with a mechanical connector like you see over here on the right-hand side. So either way accomplishes the load path connectivity at that top wall plate to wall studs. Then we go to a header, either over a window or a door. This is illustrating a window. And while this load path is really not a required one anywhere, we still have to make sure that the sheathing is attached to the header. And so this happens to illustrate a link so that the sheathing carries and transfers any uplift load or any lateral load along the header. So there is a specified nailing here that ought to be the same nailing as you would have along the edge of a panel in a shear wall or in an uplift condition. And then to handle the uplift condition, typically what's done is a strap as you see illustrated here. So metal building connector manufacturers make straps of various lengths that have rated capacities for almost always only in tension. So these straps aren't going to really help with handling a lateral load or a shear load, but they are good in tension. And one way to handle a header is to put a strap at the end of the header to the studs that are supporting the header. As you might imagine, these headers across windows and doors are acting as beams that are resisting the wind uplift sort of in a reverse loading manner because they're being pulled up as opposed to being pushed down by compressive dead or live loads. So we have a connectivity issue that we need to make sure we handle at the end of the header to the studs that are supporting the header. Here is a strap that's installed between a header and the studs that support it. Know that when they are installed in the direction that you see this one installed in, there is going to be a reduction in the load of the actual header installed. These straps are tested in a perfectly vertical direction, so the tested or the rated loads are what you would have here if this strap was straight up and down. We're seeing a reduced load capacity in this particular strap. Now we've taken the load down the header or at the header to the wall, and we now need to continue that to the floor. So we're down still beside the window. You see in this graphic an illustration of the bottom of the window, the sill of the window. And so our load path now continues down the wall to the floor beam. So in this particular case, this uplift capacity is being handled, or uplift requirement is being handled in this illustration by two metal straps to resist the uplift on this floor, on this wall system. When you go and use the wood frame construction manual and look at the loads on uplift from the effect of a roof in 1 story or a roof in 2 stories, the loads have been adequately reduced to cover the weight of the floors and the walls that are attached to them. So just recognize that you are using the loads that have already been reduced, if you will, because you have the added benefit of using the weight to resist the uplift. So using the loads out of the manual should get you the correct uplift answers here when you look at this particular connection. The floor framing to the support beam is typically handled with a twisted strap like you see here. This will help keep the floor system in place, and in fact some of these connectors do have capacities in more than one direction. So look at the load that occurs at this floor framing to the foundation method, if you will, and pick the right connector when you see loads in this particular location. I'm going to talk a little bit more about floor to foundation connections here in a little bit, and certainly in the last webinar, since that particular load carrying element's not really discussed in very many places. So now if we have a pile supported foundation, we have carried the load in the wall system to the floor system with these straps, and we've carried the load into this floor system. We have held the floor system down to the beam with this connector, and so now what we have to do is we have to make sure that the beam, the girder, is attached to the pile. So our last element of making sure that this vertical load is carried into the foundation are these bolts that bolt the girder or the beam to the pile. There is a graphic in the manual you see illustrated here, but there are a lot of variations on wall to foundation connections. You could have a sill attached to the foundation. You could have a band joist that acts as a beam and spans across piers or piles. You could cantilever over the wall. You could have a band joist that behaves like a ledger board. There's lots of ways to handle the foundation, the floor framing to the foundation connection, and each one of them requires a fair amount of thought about, so how are these loads carried to the foundation, and what loads am I looking at in the manual that will equal the condition that I have. So here are a couple of examples of other ways to handle some other foundation setups. Again, this is showing us piles. So you can see here a different sort of clip from the floor system to a beam. Here you see a hold-down connector, and we'll talk about those in a little bit. You can see here that there's full blocking across the floor system so that shear load is transferred in the floor system. And you can see some connectors that have full depth blocking across them so that the shear loads can be transferred. So there's multiple issues to consider with floor to foundation connections. When we don't do it right, this is the result we get. And so obviously this lack of connectivity between a floor system and the foundation is what we're trying to avoid. Let's look at lateral loads for just a minute. We remember from last week we were talking about how lateral loads are carried through floor and roof diaphragms, and those diaphragms take loads into shear walls. There are boundary edges, blocking, and layout panel conditions that are all covered in the wood frame construction manual with nailing patterns and load capacities for each one of these different types of diaphragms. Again, just to recover or recall what we did last week, we have wind that hits this particular diaphragm coming down from the top, and when it does, the diaphragm acts like a really deep beam and causes tension out here on this back side of the diaphragm. When that tension occurs, it tends to pull the two parts of the wall apart. Now remember, this is a floor diaphragm or a roof diaphragm. This connection here is the diaphragm to the wall. And so this is why there are double top plate requirements for splices with lengths of the splice and the nailing pattern is to resist this tension in this deep beam of this diaphragm. So when this load is collected into the diaphragm, reaction goes to shear walls here along, in this case, the left and the right side. We saw this graphic last week too. This is just another illustration of wind hitting the left-hand wall and going into the diaphragm, and that diaphragm load being transferred into the shear walls that are here along the edge. There are a couple of shear wall methods, perforated, segmented, and then one we're not going to talk at all about really, but it's trying to develop shear transfer around the openings. Almost no practitioner uses that method that I know of. It's too complicated and takes too much time. But there are tables to use for perforated and segmented shear walls. A lot of this information is covered in the wood frame construction manual's commentary for wind and seismic design, and you see the section reference there. You can also use wood structural panels for both shear and uplift, and there are tables in the manual and discussion about how to do that. So let's look at both methods here real quickly. This is a perforated shear wall method. Perforated means there's holes in the shear wall elements. And you can see the holes in this particular illustration. Don't pay any attention to the loads. This again comes from a particular FEMA manual. But the perforations in the panel, in the shear wall, mean that each element, each segment of the shear wall needs to be nailed in accordance with the nailing schedule for those shear wall elements, and they need to have resistance to tension and compression at the end of each segment. So what that means is a hold-down connector. Every place you see a T and a C is a hold-down connector in this wall. There are limitations on the ratio of these panel widths to panel heights, and this illustrates for a 10-foot wall panel the limitation on the width is 3 feet. So this is the perforated method. It means lots of hold-downs. In this particular wall, again, it means 6 hold-downs. And the difficulty here in real construction is that you have to pretty much align these hold downs for tension and compression either at piles, or you're transferring a load, a compression or a tension load, into a beam that's not at a pile. So it's an important consideration there. Here happens to be an uplift and lateral failure of a really small element of a shear wall. You can see when it started to overturn, it pulled right out of the concrete that was holding it. And this is a rod that's intended to be a hold down from top of the building to the bottom. You can see it didn't do a very good job. This is an illustration of a hold down that's in the wood frame construction manual. It illustrates how these are connected and the size of the lumber in the corners that need to be able to resist the kinds of loads on these hold downs. And these hold down loads are in the range of thousands of pounds, so they're not inconsequential. This is a nailing schedule or or panel sheathing for shear and uplift. Tells you how many nails you need and what the resistance is for various wind speeds. I'm not going to go into this in any detail, but know that there is this table in the wood frame construction manual if you want to use wall sheathing to resist both shear and uplift. I will tell you it takes a lot of nails to use it for both, but it is possible certainly in lower wind speed areas. And then there's a segmented shear wall sheathing method that tells you what the minimum height of full height sheathing on exterior walls is perpendicular to various building dimensions. So you see the illustrations over here in the left-hand column with building dimensions here in this column, and it will tell you what the minimum height of that sheathing needs to be in order to resist shear across these various wind speeds. So there is a segmented shear wall table and nailing requirements that are covered in the wood frame construction manual. And when we don't have enough shear walls, I mean, one of the ways to handle it is, some people call these portal frames. The metal building industry would call them portal frames. But when there are big holes in the walls to be able that you have to use to resist lateral loads, sometimes we have to revert to designing moment frames. And so this is just an illustration of a moment frame in a coastal building. You can see the water is to us in terms of the location of the water here to this building. So if you had a lateral wind load that would come across either side here, there's not a lot of width in this building to take the shear in, and that was the reason why this steel moment frame had to be installed in that huge window opening that you see in this photograph. So just a summary. We have vertical loads that need to be covered that start from the roof and go up, and then they need to continue down the path of the building, following where obviously the connections and the materials are, till we get that load all the way into the ground. And then we have the same issue with lateral loads. We have a load applied. In this case it's wind, and it's showing at the top of a wall, and we carry that load through the shear wall area into hold downs that are connected to beams that take the load into the soil. So let me stop there, see if there are any questions. We got a lot of questions last week that I didn't answer on air, but we really appreciate all the good questions. So let me stop and see if there are some questions.
Bill, we did have a question come in here that you might address, and that is, what is the difference between a collar tie and a rafter tie?
A rafter tie and a collar tie, there really is no difference. There definitely is a difference between rafter or collar ties and ceiling joists, although sometimes they can be the same. So typically rafter and collar ties are placed about 1/3 down the height of the difference between the roof ridge and the top of the wall plate, and that resists the kicking out of the roof from a lateral load. So they are required, and there are formulas in the wood frame construction manual actually that will allow you to calculate the tension that exists between the connection of a collar tie or a rafter tie and the rafter itself. So it would tell you how many nails you would need and what the size of that collar or rafter tie are. But to me, a collar and a rafter tie are the same thing. It could be different than a ceiling joist, though.
Very good. Thanks, Bill. Here's another question. With nail guns being so popular, would you like to say a word about the nailing as prescribed in the wood frame construction manual and what we might find actually being installed with nail guns?
I probably can't say just one word about it. I guess what I would say is that the capacities or the resistances that are suggested in the wood frame construction manual are based on a certain nail size and length. So many of the tables you will see say use 8-penny or 10-penny and use common or use box. The National Design Spec for wood has resistance capacities for certainly both of those nail sizes based on their diameter and their length. And what I feel like designers need to do is, when a nail gun nail is going to be used, get some information from the nail gun supplier about the nails that they use for their guns, and find the same sort of resistances in using those products. So if you use a nail gun nail, find out what the resistance is for that size, or the resistance per inch of the length of the nail. The providers, the sellers of those products may have tables these days that I haven't seen about how to use their products with the loads in the wood frame construction manual. That connection I'm not sure about. But I would not just use an 8-penny nail from a nail gun supplier and assume the capacity is the same as an 8-penny common nail.
Okay, thank you, Bill. Here's another question. Can moment frames be engineered, or are they typically, or can they be proprietary?
The answer is both. I have engineered some and had them built in the field, and there are providers of moment frames that have proprietary products with tabulated loads for them. So I know Simpson has a whole table of shear wall, moment frame values. Those moment frames are designed to fit into normal wood framing dimensions. They are, I think, mostly bolted connections. So you can do both, or either. You can buy a proprietary product, or you can have one made. The proprietary products will come with limitations, as you might imagine, heights of walls and loads, and certainly thicknesses depending on what the wall thickness is. So you just obviously have to meet the prescription of what their proprietary requirements are. But you can do either.
Okay, thank you, Bill. You did talk a lot about the connection between the roof framing and the top of the wall. I wonder, it might be a good idea just to review us on the directions of the load that need to be considered there.
Okay, and I spent a lot of time on it primarily because that's where we see the most failures in high wind events, is we see failures between some element of the roof and the exterior walls. So there are 3 load directions to be concerned about and to provide a way to connect the roof to resist. Uplift, a lateral load which is perpendicular to the plane of the wall, and the shear load which is parallel to the direction of the wall. So 3 different directions. They don't have to all be handled by the same connector or the same method, but they all 3 need to be considered.
Okay, great. We had a follow-up question, Bill, on the moment frame question, particularly about wood moment frames. Those also can be engineered, I'm assuming?
Wood moment frames are really tough to make happen. It's hard to get a moment connection in between 2 pieces of wood. Now, some of this answer probably ought to be answered by the American Wood Council folks as opposed to me. But most of the guidance that I get as a practicing professional engineer is that that's a really tough connection to make. And as far as I know, there's no proprietary product around that would actually make or improve the moment connection between 2 pieces of wood. So most of the moment connections that I have been involved in or seen work are all made out of steel. So the moment frame is actually a steel frame embedded in a wood wall, because there we don't have problems with making moment frame connections. We can do that with welding or sometimes bolting. So I think that's probably where I ought to stop with that answer.
Okay. All right. Yeah, that might be something someone might want to follow up with our technical helpline.
Right.
Could you expand just a little bit on segmented versus perforated shear wall methods? That's another question that came through.
Well, the 2 different methods, the segmented shear wall method recognizes the fact, at least in my practitioner language, it recognizes that wood sheathing over a wood frame wall, wall sheathing over a wood frame wall, is nailed in lots of different places, not just along the segments that are perforated, if you will. So there's nailing at the top of window and door headers. There's certainly nailing of the sheathing to the wall around the bottom of the window header. And all of those areas should be and could be incorporated and included as part of a shear wall. And so the segmented method that is described in the manual takes advantage of that consideration. The perforated method just assumes you've punched such large holes in the shear wall that you really just have to consider the elements that have solid sheathing from the bottom of the wall to the top of the wall. And so the advantage of a segmented wall is you can eliminate a lot of hold downs as long as you can get enough capacity and enough full height area of a segmented shear wall. You really only need hold downs typically at the ends of those segmented walls, whereas in a perforated wall you need hold downs at the edge or end of every perforation. So it requires more hold downs, which equates to money, obviously, in a perforated wall than a segmented wall.
Okay, great. One more question here. Is there are there minimum aspect ratios for shear walls in the wood frame construction manual?
There are. Somebody's testing the limitations of my remembrance of exactly what those ratios are. I think that the ratio is in the range of 2.5 to 1. So you could have a wall that's 10 feet high, then you'd need a segment of a wall or a part of a perforated shear wall that would have to be at least 2.5 feet wide.
Bill, I just got a chat from a buddy here. 3.5 to 1 typically in most circumstances, but for seismic 2 to 1 typically is what he's responding here.
I knew you guys would know that answer, so thank you.
Okay. All right. I think we're out of time, and it was a great presentation. Thank you, Bill. The final slide is up there, just a few reminders. You will be receiving the email with the links for the survey and the certificate information. The certificates will come to you in about 2 weeks. We do have a couple more wood frame construction manual series webinars coming up, the last 2 of this series, next Wednesday and the following Wednesday. And then we have a couple other webinars, one on prescriptive residential wood decks and another on code-conforming wood design, which is a broad treatment of using wood in the International Building Code. So we certainly